Hello, this is the third in a series of short webinars about the VelPAK and Velit wizard tool. The previous webinars gave an overview of how the wizard works and how to calibrate seismic velocities to well thicknesses for depth conversion. This webinar dives deeper into one aspect of the software, which is using numerical optimization to determine stable velocity functions from well data. This technique is also suitable for utilizing pseudo-well data derived from seismic data. We also look at how we can leverage this technique to bring a space-variant component into the velocity model. So what is numerical optimization? It is a widely used mathematical technique to determine the best coefficients for a function that best match a set of measurements. There are many types of numerical optimization approaches, each with different merits, but the details aren't particularly important. All we need is a bunch of data and a function to fit to that data. One of the most frequently used functions is the linear V0kz method that relates velocity v at a given depth z by the equation v equals v0 plus kz, where v0 is the intercept of the line at zero depth and k is the gradient of the line. The v0kz function is popular because within a defined layer it often reflects the increase of velocity with the depth of burial, with the depth ranges of normal exploration, and it is a stable function which is quite forgiving of small mispicks of tops or interpretation. If we have velocity logs for our well data, we have measured velocity data against depth, either from sonic logs or checkshots or VSP surveys. This data is ideal for determining the v0 and k parameters for our linear function. However, as you can see on the slide, not all velocity functions are linear. Here are 4 examples in use by our customers: the Houston, Faust, Slotnick and hyperbolic tangent techniques, each showing a velocity versus depth plot for sample data, the functions, and the curve fitted to the data with the equation coefficients determined by numerical optimization. These curves tend to be fairly specialist, but they demonstrate that as long as you have 2 unknowns, the optimizer in the software can determine those which best fit the input data. For example, in the Faust function, we have measured values for the velocity v and depth z, so Optimizer can provide the best values for the coefficients a and m that fit the measured data. In this webinar we will focus on the v0kz method, but bear in mind the use isn't restricted to this equation solely. So how is the Optimizer implemented within the software? We actually take 2 approaches, the best fit function and the minimized residual function. Both work well by well and then combine the results to give a layer fit or a layer residual result. Firstly, we'll look at the layer fit approach. The actual algorithm used is somewhat complicated and works in a rather more detailed level than is portrayed in the slide here. Essentially, a series of v0 and k pairs that best satisfy the well velocity log function are tested. A depth conversion is made using these values, and the resultant depth of the predicted base of the layer is compared to the actual depth of the layer, indicated by the formation top. Numerical optimization is employed to minimize these errors. An optimal v0 and k pair for the well is computed, which we call the well's best fit function. This process is repeated for all of the wells for the layer, and a v0 and k pair for the layer is derived, which we call the layer fit. The other approach is not to use the velocity, checkshot or time curve data at all, as you may not have that information for many or indeed any wells. Instead, matching pairs to formation top depths and interpretation grid times are used. The v0k parameter space is systematically tested with the v0kz depth domain equation to find the v0k pair that will correctly predict the bottom depth of the layer. Obviously, in this scenario, there are an infinite number of v0 and k values that could cause the predicted depth to tie the depth of the formation top at the bottom of the layer. So this method is far less stable than the fit method mentioned before. With even just one well, the fit method is very stable, whereas the more wells you use for the residual method, the better the result will be. However, the residual method does have the advantage of being quicker to run, and you can often use many more wells than you might have for the fit method. All of the theory just discussed might suggest that optimization is difficult to prepare data for, complex to use, and hard to interpret the result. In fact, the wizard makes running the optimization very simple. A few clicks is all you need. For using the fit method, all you need is your layer model defined by formation tops in the well, and sonic or checkshot data for one or more wells. Naturally, the velocity logs need to be in a good shape, with spikes and sonic cycle skips edited out. For the residual method, you don't even need logs, just grids and formation tops, which you need for most of the other depth conversion methods anyway. We also need a parameter space within which we expect our V0 and K parameters to lie. However, the wizard estimates this for us automatically. Once we have seen the optimization results, we need to decide whether we would like to hold the K value constant, compute the corresponding V0 for each well, then depth convert using the mapped V0 values and a constant K. So let's see this in action in a live demo. This model is data from the Galleon field in the southern North Sea, courtesy of Shell UK. If I review the well data, we have a clear linear velocity trend with depth, so using a V0K method would appear to be appropriate. This seems to be consistent between the wells, so if I open up the well options here on the left hand side and scroll down and select well 4815A9, we can see that there. I can also see this in well 4820-1. We're going to run the optimize through the wizard, and although it can be of course run via workflows or manually, I'm going to show you how easy it is to run it through using the wizard module. Here I'll select on the wizard, and you'll see that it takes a couple of moments to load, and we come to the wizard tool. Here on the wizard tool I'm going to press the run button on the first layer to start the wizard for the first event. We're presented with the usual choice of options, and here in this example I'm going to use the option optimize and then press the next button. The data in the model is then verified as OK, so we can press next to proceed to the next page. We are presented with the options relating to how the optimization should work. The first set of options allows you to run the optimization from the seismic datum, an arbitrary datum, or factor in uplift. Remember the V equals V0 plus KZ equation. We assumed the V0 value was at the surface datum, but in certain circumstances, such as very deep water, it may be better to take the V0 datum as the seabed. If there's been uplift, so that the well velocities appear to be higher than they should for a given depth, then we may wish to incorporate uplift into the V0 KZ equation. The uplift factor may be parameterized and entered here to compensate for uplift in the V and 0 and K computation. In this example, we will keep it simple as we have no uplift or datum issues, and though it is a marine project, the water is very, very shallow. It's about 15 to 20 meters in depth. If we have a look down here, the second group allows us to select whether we are going to use the fit or residual methods as discussed previously. This time I'll set the option to fit to wells, but we will revisit and use the residual option later. As always, you can review the help screen for further information on each of these options. You can scroll down here so that you can see that available. So now press next. On pressing next, some computation is performed and we are taken to the optimized parameter space screen. The parameter space for the optimization can be defined here, but as you can see the software has made a quick estimate of the ranges to use. I'll press the Run Optimize button and set the optimizer to work. So as you can see, I'll just move across here and press this like so. The process takes a few moments, and with a model with lots of wells and logs, it could take several minutes to run. The results are displayed in the Optimize window, so what I'll do here is I'll dock this adjacent to the wizard and collapse the help display to maximize the display area. So here I can left click and drag and hold. I can then press the button at the top to close the help and drag that across to maximize the display area. What this is showing us is on the x-axis of the graph we are looking at the V0 parameter space, and the y-axis is the K parameter space. I'd like the action centered on the plot, so I'll adjust that like so. So I can hold in the middle mouse button and drag, and then I can also zoom out as well. As we can see, the optimized parameter space values haven't yet been updated in the software, so we just need to press the two green arrows here to update the values. And then I'll select the Run Optimize. You can see here that the values are V0 from about 10 to 4150 in 50 increments, and K values from about 0 to 3, also in 50 increments. I can manually adjust the parameter space by typing in new values, or as you've seen me just do, I can zoom into the area I want and press the values with the green buttons. And using that refresh from model button transfers to the new region across the wizard. Now the lines on the plot are more centered so that we can see all of the pink values going through the center. Each pink line represents a well, with any V0K pairing along that line representing the best fit for the well data to the V0K function. Now here on the well display, I can show you that the pink dot represents the optimal V0K value for that well, and the black line represents the well currently shown in the well module. If I change the well module and step forward and backward through the wells, you can see this update, or here you can see me selecting well 4814-2 for example, and you can see on the display that the black line updates. If you just had one well, the single pink dot V0K value would be the one to use. However, we have multiple wells here. The good news is that the well lines converge and there are no obvious outliers. The mean of the well lines is plotted as the yellow line, and the optimal V0K that satisfies all wells is posted as the yellow dot, right in the center of the display. The V0K values are also shown on the wizard display, which are just under the information. The contour coloring of fit display is a measure of goodness of fit of the function to the data. The smaller the value, the better the fit. And you can notice that we have a solution trough in the center, with any V0K pairing in this space having a similar goodness of fit. So everything looks fairly okay, but it's always worth zooming out so that we can see if there are any outliers in the data set. Here if I zoom out quite a lot, you can see that there's a pink dot at the bottom of the screen. We can investigate this dot using the point pick option, and here if I look on the well display, we can see that it's the velocity log for well 4820B-6. We can see only a very short log portion over layer 1, and the trend is counter to the trend in the other wells, simply because it is not logged over the bulk of the formation. Therefore it seems reasonable to exclude this well for the layer. So here I can set the icon to point edit, zoom out, select the point edit icon and click on the point and press OK to toggle the well off for the current layer only. I can then click back on the wizard and click on Run Optimize to regenerate the results excluding this well. You'll see the V0 and K values posted in the wizard window change slightly. Here we can check for any other outlying wells before pressing next in the wizard to proceed. Here we've got two options. The first option allows you to override the computed V0K values. You can use a user value on the optimized display by using the user edit icon and clicking on the optimized plot. I can fine-tune the value in the pop-up. If you toggle on the override option, the V0 and K value selected is used. If you toggle it off, it'll use the computed value, which is what I want to do in this project. The next option allows me to fix K and contour V0. Often the velocity gradient is constant in a given formation, so if we choose to fix K to its computed or selected value, we can find the corresponding V0 value for each well and map that. The wizard allows us to use kriging for mapping of V0 values, though if you drive the software through the workflows or by hand, you do have more options. How the V0 value is computed is up to you. You can choose to minimize by residual depth, in which the V0 value for a given K is computed as one that will best tie the depth converted time grid. You can also minimize by fit error, in which case the time grid is completely ignored and the v0 that best ties the log data for that k is used. This means that the velocity function computed is completely independent of any seismic interpretation, which can be quite important to bear in mind depending on your project objectives. The default kriging range covers the longest diagonal of the grid area by default, but of course can be adjusted. Pressing the Generate v0 grid and display it results in the v0 map being displayed. In this project, I've not got a lot of wells to make a meaningful map, so I'll turn off the Fix K option and use the space invariant v0 and k parameter instead. As you can see, I just pressed Next on the wizard, and you can see that the displays are updating accordingly. Here we have the error correction option, and we have the ability to generate an error correction grid. However, before we do that, let's have a look on the surface display and zoom in like so. Here I can see the mistie values on the surface map. That is the difference between the formation top in depth and the depth grid predicted by our method. Let's look at the values. Here, before I do that, I can select the option at the top, and we can make the display a little easier to read. So I can click on Display Types, and then it removes the background color map. Here we can see the values. So we have 99, 70, 21, 18, 90. In fact, all the values are negative. But don't panic, this is not a bad depth conversion. We can see these displayed graphically on the well display. Here I'll just select the well display, and you can see that the red point shows the predicted depth of the depth converted time grid using our selected method. What this is saying is that the v0k from the wells, which is reasonably consistent, is running a little faster compared to the seismic image, assuming that there are no mispicks of the seismic events, etc. in this case. This is hardly surprising. Seismic velocities generally bear little relation to true vertical velocities measured in boreholes, and it's exactly why we need to use software like Velit VelPAK. The seismic needs to be squeezed a little to tie the well formation tops. I'll toggle the option on to generate the error correction grid, and set the kriging range to around 4 kilometers around the well location. Then I'll create a preview of it. Here I'll just go up and select the surface tab at the top here, and away from the wells we can see that there's a mean of the values being about 62 meters. We'll incorporate this correction into the depth conversion by pressing Next, then working through to completion of the wizard. I can review all of the data for the optimization on the Optimize Data tab. The fit column indicates which wells have been used for the optimization result and which have been turned off. Note that if there are no points in the layer, i.e. velocity log samples, that well obviously won't be used for the fit method either. We can see we have a lot of wells without logs, so let's utilize those using the optimization in the next layer. I'll run the wizard again for layer 2 by pressing Next, and here I'll select the Run option on the second layer, and again choose the Optimize and press Next, and then step through again by pressing Next. Here we can see the Fit to Well curve display on the Optimize tab, and I'm instead going to now select the Minimize Residual Tie with Well Formation Tops option and press Next again. This time the wells are actually drawn in blue, and these are the well residuals. The layer residual contour plot this time is in RMS values of residual errors in meters in this project. Here on the screen you can see the values posted on the contours like so. We also have the optimized parameter space listed at the top. So I'll press Run Optimize, and here we see a convergence of the blue lines running through the central solution trough. However, there is one glaring outlying well. I can select Point Pick and select this well, and by selecting the well display we can see that it's well 4820A-2. By looking in the well window we can see that we have problems with the layer definition for this well, with a top missing. So on the optimized display I'll edit the point and select the point edit here and turn off that well by pressing OK. I'll then click on the wizard and select Run Optimize again to recompute. As this updates, we can now see that the wells converge with no outliers, so we can quickly step through. It's worth remembering that the residual method doesn't use the log data at all and is prone to instability, so the more wells you have the better, and ensure they converge. If they don't, the method might be invalid to use. As I step through the wizard, you see the options are the same as using the fit method. Again, I'm not going to map V0, so I'll have the residuals between the depth converted surface and the tops. If I generate the residual grid using the same 4 kilometer range, like so, I'll click on Generate Error Correction Grid and see the software update. As it processes, I'll now select the Surface tab and I can zoom in like so to see the values a little more clearly, and selecting the drop down menu here, click on the display type and select Basic. Here you can see that the mean residual correction is around 0. If you recall that the fit method had larger errors. Therefore, the residual method ties the well tops better than the fit method, but it doesn't necessarily mean the velocity function is better than the fit method, just because the numbers are smaller. The fit method honours the velocities in the well logs. The residual method aims to tie the depth converted surface to the tops. Which is better depends entirely upon your objectives. And I'll just select Next to finish the wizard for the second layer. So that's a quick overview of using the powerful optimization tool. You can find out more by using the Help Contents menu option and reading the Optimize module introduction. Thank you for watching this webinar. If you have any questions, please do not hesitate to contact us at support@equipoisesoftware.com. Please also check our website www.depthconversion.com for more webinars on software features, or alternatively check our YouTube channel Equipoise Software.